Here's an example of using Chauvenet's criteria to determine what data points in a data set are outliers. While this is maybe not a common scenario that you would run into collecting data, it is pretty good to kind of illustrate some of the weaknesses or maybe some of the limitations of this technique of using Chauvenet's criteria to exclude outliers from a data set. So what we've done since spring of 2020 is we have passed out a whole bunch of nickels to all the students in the class. We had them flip the nickels 10 times and keep track of how many heads they got out of the 10 flips. So what you see here on the histogram is the number of times that someone got 4 heads out of 10. We had 107 students get 4 heads out of 10 flips. And so that's how this specific bar in the histogram was generated. And so you can see if we went back to one of the previous semesters, we went around the room and we collected the data and put it in here. And then we have summarized all of the data from all previous semesters into this one table here. So you can see that we have had 494 data points that we have collected. Now, since there's an infinite number of data points that are available here, we're going to use sample statistics because we've got 494, which is much, much less than infinity number of data points. So we've got the event, number of times we got heads out of 10 flips, and then we have the occurrences. So how many people in the classes got 3 heads out of 10 flips. And then we've got percentage of total occurrences. So this is essentially our probability. We have 53 times someone got a 3 out of 10, 3 out of 10 flips, they got heads, divided by the total occurrences that happened. And so that is the probability of getting a 3 out of 10 is 0.107 or 10.7%. And then the deviation is this specific data point. How far away from the mean is that specific data point? So the deviation, we then square it, and then we can use that to calculate the standard deviation. So if we have all these deviations squared, now we can take those deviations and put them in this equation. You can see we've got n minus 1 here because we're using sample statistics. So that's pretty important for us to take note of. So we've got our mean, standard deviation, and number of samples. And from there, we can actually calculate the Chauvenet's criterion and determine which of these data points are outliers. And so I've got these gray bars and they're just sitting here, but we are going to place these gray bars on here to illustrate where that D max value is, or where that boundary is that we're saying anything beyond this boundary is going to be outside of the data set or is an outlier. So as a quick reminder, what we're looking at here is this S. So we put this D max and we say anything that falls outside of this D max falls within this category of probability that we're calling S. And since we use table 3.2, then we have half of the probability. That's where this 0.5 comes from. So we have half of the probability minus what we are interested in, which is this area out here. So then we can say anything that falls outside of here is an outlier. And then the Z is what number of standard deviations. And we use the table to determine the probability and the Z value associated with that probability. Okay, so going back to this example, we have our S value. Now we calculated that S value by doing 1 divided by 4 times the number of samples. And that number is what the contribution of Chauvenet was. He performed many, many experiments and determined that this factor, this 1 over 4n, accounts for one tail. And the reason we do one tail is because typically we're using that table out of the book to look up the probability, which is the area under the curve of half of the curve. And so this S is the outside portion. So it's this right here. And it is equal to 1 over 4n. So this is Chauvenet's criteria that we are utilizing to determine which of these points are outliers. So here's the 1 over 4 times the number of samples. And so that's going to set our S, and that is the probability under the curve that we're interested in. So then from there, we can get our D max. And the D max here You could look it up at the table, but I actually am using an Excel function here, so I've got a little bit better resolution than the table can provide. And then I have my high and my low event. And so what I'm doing here is I am applying those equations that we looked at right here, this equation right here, and we reformulated it and laid it out into this format. So this right here is exactly the equation that we're using right here. So that high event, we're taking our Dmax value, we're taking our mean and we're subtracting off of that our Dmax value, multiplying that by our standard deviation. And so that is going to give us what our high event is. So anything greater than 6.47, we're going to throw that out and say it's an outlier. So let's move our thing over here to 6.47, which is probably about right here. So anything greater than that, we're going to throw it away. And on the low side, we're doing the exact same thing, but we're doing minus. So we take our mean and we're subtracting off our standard deviation times our Dmax. And so the value of that is 3.76. So let's go over here to 3.76 is probably somewhere in here. So now anything below this is going to be an outlier according to Chauvenet's criteria. So it does look like it's a little bit imbalanced. And so this is a cautionary tale that when we are throwing data out, we can't just blindly throw it out and assume that the model is correct that we're using. We need to make sure that we understand what data we're throwing out and really convince ourselves that it is the correct data to throw out. Because if you remember, we are engineers and we are the ones doing the measurements here in this class, and probably in our career we're going to be doing measurements, and those measurements we're going to report them in some format out to the public, either within our company or maybe out to the general public if we work in, say, a research institution or something like that, and we're doing fundamental research. And so the data that we are providing to customers or design engineers or people like that, they are depending on us to make these educated decisions on what they can expect. And so we give them a measurement plus or minus an uncertainty. And so what we're doing here is we're saying the data that we collected to get to that number and to get to that uncertainty number, we're trying to determine if there are outliers in the data set that are true outliers. So we got to be real cautious when we throw away data. So hopefully you can feel that it is very important for us to be convinced that the data that we are collecting, the data that we are throwing away is truly an outlier. Okay, so based on this experiment that we've done in class for several semesters here, it looks like let's just make sure our bounds are correct. So anything 3 and below we're throwing out, and then anything 7 and above we're throwing out. So we are throwing out 166 data points, which is 33.6% of the total. And so that's quite a bit of data that we're throwing out. And so we want to be really cautious here. The other thing that I want to point out here is look at this, how close it looks like a Gaussian distribution. So how can we improve this experiment? How could we make this experiment be more closely represented by a Gaussian distribution, which may influence the outliers that we are predicting using Chauvenet's? So think about it for a second. Hopefully your thought is, instead of having the students, we've got 494 data points, but we only had them flip it 10 times. If we remember from our slides on the same topic, if we had them flip it more coins per data set, so each time we took a sample, instead of saying flip it 10 times, maybe flip it 30 times, or maybe flip it 100 times, then we get more and more closely represented by a Gaussian distribution. Our data set does. And so if we were to do this again, we could maybe change this number from 10 to 50 to 100, and that's going to make it more Gaussian, and it's probably going to shift these values. So then we're getting rid of less data, maybe something a little bit more like this, and maybe going to give us a little bit higher degree of confidence that that the outliers truly are outliers, and we're not impacting the results that we're going to be presenting to the users of our data. look at a more Gaussian distribution hypothetical scenario. So instead of flipping a coin 10 times, what I've done here in this scenario is I said, let's just assume that they have flipped it 30 times, and I made up data points, but hopefully this will still illustrate what we're talking about here. So same exact table that we've had. Let's clean this up just a little bit. These occurrences, we probably don't need all of this resolution. It probably is nonsensical to us anyway. So again, we are going to place these Dmax boundaries based on Chauvinet's criteria. So we have 820 data points. Our mean and our standard deviation are calculated by the numbers up in this table. And our standard deviation is based off of those deviations squared divided by our number of samples minus 1, because we have sample statistics we're using here. So S is, in this case, 1 divided by 4 times 820. And so in this case, we've got an S of 0.0003049. And so then we take that, and if we were using the equations out of the book, it would be the D, see if I've got that equation handy here, this right here. So our D max would be our 0.5 minus that S, and then we'd from there be able to calculate out what our Z value is based off of the table. Instead, I'm using the function that's built into Excel to figure out what that value is. So our D max is 3.4272. So that makes our high event 20.62 and our low event 9.42. So let's go up and set these. So 20.62, so anything greater than 20.62. And again, we have discrete values. So 20.62 is probably somewhere in here. So that means 21 through 30 we're going to throw away. And on the low side, 9.24. So anything smaller than 9.24, so that's probably somewhere in here. So that means 1 through 9 we're going to throw away. So let's see how many data points we're throwing away now. See if we have improved this at all. Looks like we need to adjust this, so it is down here. We threw away 21 through 30, and then 1 through 9. So now we're throwing away 147 data points out of 820, which is 17.9%. So it did get better by tossing the coin 30 times in this hypothetical scenario. It does look more Gaussian, and it also makes us a little bit more comfortable throwing away those outliers because it's a smaller percentage of the overall data. Hopefully that helped illustrate it a little bit better. Now let's compare for just a second the difference between using the Excel function and using the table to look up the values for the Dmax. And so this right here, let's use the table and see what the difference is. So Dmax is equal to Z times 0.5 minus S. And so again, this is because we're dealing with half of the table. So we've got our 0.5 minus S. Let's just throw that equation in here. So we'll just add it in right here. Is equal to 0.5 minus our S. So that is going to be 0.499. So that's the probability that we could use in our Z table to then look it up. So let's see, insert. And so let's do our Dmax, D. Here, let's copy this, Control C, Control V, Dmax. And we'll say this is from table 3.2. Let's be consistent here. From table 3.2, and I will look up our table 3.2. Okay, so here's our table 3.2, and we've got 0.4996. So if we have 0.499, we'll zoom in on this a little bit. You can see this entire row, there's many of them that are 0.4996. So let's zoom out just a little bit. We got 0.4996 up to here. So this is a pretty big range. And so then we'd need a little bit better resolution. And why is that true? Why do we have so many values that are so closely related? Well, it's because we're looking at the tail end. So we've got this tail, and the tail kind of runs out here, and the values become very similar to one another. So there's very little change in our signal as we change the input. And so the number is going to be 3.3 and then some change on that. So then how do we get a little bit closer? How do we get 3.3 something? So we've got 0.4996, 9. So the next data point is so close to 0.4997 that you could probably argue that it's right out here. So 3.38 or 3.39. So if we put that in here, 3.39, or maybe you could say 89 or something like that. Something, I don't know if we can be that confident. So 3.39. Let's clean that up a bit so we're not confusing our reader by giving too many significant digits. So then let's add in here a couple more. And so now with the same equation, oops, Control C, Control V is what I'm doing. So let's move these around and make sure we've got them looking at the right values. Okay, so let's adjust our equations here. So we've got our mean plus our Dmax from the table times our standard deviation. So 20.55, and then on the low event, we have our mean, whoops, our mean minus our Dmax times our standard deviation. So look at that. Because we use the table, maybe I'll clean this up a little here. Okay, so now that we have these equations put in here, we have our Dmax that we use the Excel function from, and then we looked up the Dmax from the table of 3.39, and we had to do a little bit of linear interpolation in our head and kind of rounded, and we had justification for why we went to 3.39. You can see it is a little different than what we get from the Excel. And the impact of that on the high event, we are now throwing out 20.55, and on the low, we're throwing out 9.30. So if we go up here to our table, we create some new lines here, and let's format them just a little bit different. Let's do a blue color. Okay, so now let's place these. So from the table, we have our blue color, 20.55, which is going to be probably right there. And we have 9.30, which is going to be right there. So you can see it's almost no different using the table versus having the higher resolution of Excel. And the overall discarded number of points did not change because we have discrete values up here. So we don't have a point in between 20.55 and 20.62, and we don't have a point between 9.3 and 9.24. And so the result did not even change based on using the table versus using the higher resolution option of Excel. Hopefully that illustration clarified a few things for you.